Today's talk is about certain aspects of the execution model used by the mill architecture. The mill is a family of CPU designs, family in the sense of the 360. Due to the advances in the architecture, it's a commercial product, or we hope it will be. It's still in development. And it offers a 10x power performance advantage over existing architectures. This is an architectural advance. It is not a circuit advance. It is not a fab advance. We use exactly the same run-of-the-fab circuits and standard rules as anybody else. It is an architectural advantage. It does so without requiring a rewrite of your program. It does so without requiring multiple core or multi-programming. You can, of course, multi-core and multi-program mills just like anything else, and it's just as much a pain in the butt on a mill as it is on anybody else. This particular talk, I have to back up a little bit and speak a little bit to describe the way data is moved back and forth internally to the machine. The mill has no general registers. It uses a different device, and I have to explain that a bit. This was actually covered in considerably greater depth roughly a year ago, May or thereabouts, here, and the complete talk of that is both available on the 380 website and on ours, and much greater detail at other locations. Given that as a background, I'll talk a bit about how phasing permits us to triple the effective ILP, instruction level parallelism, of existing codes, how we are able to combine the computational capacity of the machine so as to support novel operations that a conventional machine cannot do. And how that gets used in order to avoid the problems using condition codes to indicate Boolean values. Lastly, I'll speak briefly on the subject of how n-way branching is performed and how when you have multiple calls in a single instruction, how these cascade. This is a series of talks. This is the 6th of them. All the prior talks videos are available on our website at that address. Those of you who are taking the class for credit, your homework assignment is to review the material at that location. There will be a test. And a caution. This talk is a gross oversimplification. The guts inside a CPU are fiendishly complicated and depend on hardware and other details that cannot be covered in a talk of this nature. Instead, I try to convey an intuitive understanding suitable for a non-specialist. You're assumed to have some idea what goes on in a CPU, but we're not going to get in any great detail. I'm open to questions after the talk, and I can go into all the detail you'll ever want, but the talk itself doesn't do that. Reality is much more complicated than this talk will indicate. We try not to oversimplify, but sometimes. So a few words on the belt. As I said, the machine has got no general registers, but you do have to get the result from one add into the multiply that you have to use the next data with, and that requires a communication device. The mill is the first of a new category of processors called a belt machine. There are numerous other categories. There are stack machines and accumulator machines and general register machines and so forth. These are categories. There's lots of different architectures within a category. There's lots of possible belt machines. The mill is one. It is a point in that design space. The communication device looks like a conveyor belt. It is a fixed length FIFO. Assume that that is a set of values sitting on the belt. A functional unit can read any position in that FIFO, pulling values off it down into the functional unit. New results always drop on the front of the belt, unconditionally. You do not specify a destination for your computation. However, it's a fixed length, so when you drop a new one on the front, well, that pushes the oldest off the back, and it is gone permanently. The functional units, there are many. The mill is a wide issue machine in the sense that a single instruction can contain many operations, like a VLIW does. Fair warning, a terminological trap here. Most people are used to thinking that an add is an instruction. Once you're in the wide issue world, an add is not an instruction. An add is an operation, and there may be a ton of other operations in the same instruction. So in this case, you can have 3 different functional units, which will be independently grabbing values off of the belt. And in due course, when those functional units are ready to retire a result, all of their results drop onto the front of the belt and push corresponding numbers of operations off the back. Addressing into the belt is addressed by relative position. So this, for example, might be an assembly language operation. This says add B3, belt position 3, to belt position 5. Note no destination. The results are implicitly dropped on the front. The B3 and B5 are there. If you think about it, you realize that B3 is the 4th most recent value to have dropped to the belt. And B5 is the 6th most recent value to have dropped to the belt. So this is temporal addressing. It is not spatial addressing. You're not saying put something in R6 and it stays in R6. This says pick up the value indicated by the temporal order in which it got originally placed upon the belt. So a consequence of this is that every time you do a new drop on the front, everybody's temporal address changes. So that, for example, if we want to reference that value 8 in red there, that is B3 now. But as soon as a few more values drop onto the belt, B3 now refers to somebody else, and that value 8 is now B6. This is a truly awful process to attempt to keep track of by hand. The mill is not designed to be an assembly language target. However, this is trivial for a compiler to keep track of, and it is no more difficult than the problems involved in, for example, register coloring and similar things for a compiler. Now, so much for the belt. Going to talk about phasing. Operations connect through data flow paths such that the result of one operation is the input to a next. And the chain of such items is a data flow, frequently a data tree, but for most of what I can show on a slide, you can only fit so much on a slide. We're going to be looking at linear data flows rather than trees. A consequence of the way the mill is organized is that we are in fact able to execute faster than the clock rate would appear to make possible. I want to emphasize that this is a programming model. The underlying reality does not have a time tunnel inside it. There is no black hole and a spinning black hole that permits you to do multiple things at once. So I will be explaining a little bit about how the hardware provides this illusion, but from the viewpoint of the running program, effectively we get a significant speed up, and you'll see how. Now, a data flow is a chain of operations which are dependencies. If there's no gap, such that the add goes directly to the multiplier, goes directly to the subtract unit, goes directly to the store unit with no time gaps at all, the fastest speed is determined by the latency of the individual operations. An add takes 1 cycle, a multiply takes 3 cycles, the subtract takes 1 cycle. Well, you know that the fastest you're going to get is it's going to take 5 cycles to get through all of that, because it's immediate, one after another. This limit, based on the propagation delay of the data that has to be passed through, is analogous to what happens in the propagation of sound in a medium like air. because the speed of sound is determined by how fast one molecule can juggle up to the next molecule, can juggle up to the next molecule. And that's determined by the characteristics of the medium, but there is an upper limit to it, which is identified in aeronautics as a Mach number, after Ernst Mach. And Mach number 1 is the speed of sound, and by analogy, Mach number 1 is the speed that a computer can execute a data flow with no gaps in the middle, just one thing going directly to the next, to the next, to the next. You might think that Mach 1 cannot be exceeded. And in fact, I'm here to show you that it can be, just in fact as you can do it in airplanes. Now, for example, let's take this as a little piece of source code. We've got a big constant there that's much too big to be done as an immediate and add operation. I'm assuming a load store architecture here, not something in which, like an x86, where you have funny extensions and huge instructions that can carry big constants, but think of your typical RISC type instruction set. And the machine code of this is, well, you're going to have some kind of an operation that builds a constant for you. Sometimes in some machines this is more than one operation in order to put it up in pieces. Other times there's some other way to do it. I'll assume the presence of a const type operation, that there's a functional unit that produces a constant. Then that has to be fed into an add, like that. And that in turn will have to be crossing a cycle boundary, because we had to first get the const, and then one cycle later the data value is available to the adder. And now once the adder's done its thing, that's going to be fed into a store unit, and there'll be another cycle boundary there. The dotted pink line in all of these slides means a cycle boundary. Anytime you see something flowing across there, it took an extra cycle. Now that's the basic model. In a VLIW, which is a wide issue machine, you can issue several operations in parallel. In fact, you might be able to have a constant, an add, and a store all in one instruction, which is a fairly typical arrangement for VLIWs. So if that's our same source code, the machine code might look like this, where an underscore there means all one instruction. So this is one instruction with 3 operations in it. We might think that, well, you can have a const feeding to an add, feeding to a store. But unfortunately, you can't do that. The whole cycle is taken up by the const, and the whole cycle is taken up by the add, and arrows don't go upwards in data flow. They only go downwards. So anytime you see an arrow going upward, that means that this is something that is physically impossible. Those paths are impossible. So what do you do? The VLIW is going to have to take 3 cycles, just like a RISC would have to take 3 cycles. The mill splits each instruction cycle into phases. These are not subclocks. We don't actually have a whole bunch of little clocks inside the big clock. There's only one big clock. So phasing is a conceptual model. That source code, again, will produce, in fact, the same machine code as the VLIW uses. Constant, add, and store, all in one instruction. The underlined recall means that this is in one instruction. There's our cycle boundaries. The const unit happens there. That feeds the add, because operations in different phases can be part of the same data flow. There's a phase boundary between the two, but not a cycle boundary. And there's a phase boundary between the add and the store. Now, this is the logical view. Physical reality is different. I used to say that when I was in the 60s. But anyway, phases execute in sequence as a data flow. And each operation in the instruction set of the machine is associated by definition to one particular phase. The results of an op, each operation can have as its input results from a prior phase. Here are your phases. The reader phase handles those things which have no inputs, constants, values read from spec regs from the scratch pad. Scratch pad we won't address, but it's temporary storage area. Op phase is all your ordinary ops, your adds and subtracts and your loads and your thises and that's. So anything in op phase can see anything that was produced in reader phase. In particular, in our example here, add can see the result of const. Call phase, function calls. Pick is the equivalent to the question mark colon operator in C. It selects one of two based on a selector value, has a phase all of its own. And writer phase are those things which are pure sinks and who accept inputs but have no output, in particular stores, branches, and things like that. So those are your basic phases. Our const, add, and store, which we had in our example code. The const is in reader phase, so it can pass data to the add, which is in op phase. And the add can pass data from op phase to writer phase. If the phases happen to be the same, you can't pass through, but you can pass to a subsequent phase in the phase order list that I just described. In the actual implementation, ops from one instruction are not issued all together the way they would be in a VLIW. That VLIW, if it said const, add, store, all of those are happening all at once in the same cycle. That's what a VLIW does. It's what it is. Not true in a mill. Instead, the ops from a single instruction are in fact issued over 3 different cycles. So, if these are my 3 instructions, in this cycle, this is instruction 1, instruction 2, instruction 3 in order in the program. In this cycle, the reader phase of instruction 1 will be the first thing that happens. Then we cross the cycle boundary. And instruction 1's op phase executes at the same time as the reader phase of instruction 2. Another cycle boundary. Instruction 1 is reached and is executing writer phase. Instruction 2 is now in its op phase doing adds and the like. And instruction 3 has just started up with whatever it's got for reader phase. And so on in the obvious way. So each instruction executes over 3 cycles, which are 1 cycle phased away from the prior and subsequent instruction. Now, one way of looking at this is that the phases form an intra-instruction software pipeline. Values get passed from one to the next over multiple cycles, but still within one instruction in the way that a software pipeline loop does. It's an analogy. It can't be pushed too far, but it's a way of thinking about it. Now, phase assignments. I alluded to this. Those things which are going to be operations which will be assigned to reader phase will be all those that don't need any inputs. They can just be done as soon as they get decoded. Op phase are those things which need to have some inputs and also produce results that somebody's going to want to produce, want to consume. And writer phase are pure sinks, things which will grab values but do not have to pass them to anybody else. There are cycle boundaries between these, and as a result, each phase can, in fact, pass to the subsequent phase, even though they are in the same instruction, because they issue at different times. How that works with a decode, on most machines, in particular most VLIWs and other wide issues, all of the operations of a single instruction are decoded simultaneously, and they're all made available to the execution unit simultaneously. Not on the mill. The mill is way too wide for that. The mill is exceptionally wide. At the high-end mill family of the mills, you can have 30 or more operations in a single instruction, all of which have to be decoded out of a variable length encoding, and there's a complete video and talk on that subject at considerable length on the site. Remember, that's your homework. Those instructions wind up being pulled up through a fetch hierarchy and placed in a microcache, which is the actual input into the decoder. So the instruction gets sent to a decoder, and that it's crossing a cycle boundary as it goes from the microcache into the decoder. Internally, in order to decode 30-plus operations, it takes the decoder 3 full cycles to be able to do that. And how it gets away with being able to do it in only 3 cycles is an interesting subject that you can read about elsewhere. Meanwhile, different parts of the instruction are available from the decoder in different cycles. Some parts are available in the very first cycle. Some parts take 2 cycles. Some parts take 3 cycles to get everything figured out. So as each piece comes out of the 3 different cycles in decode, they get fed to the execute engine. And the execute engine then winds up, dear me, 2 of the blocks are available a cycle before the others out of the 6 blocks which occur in an instruction. And they are arranged so that those things which are going to want to execute in reader phase, in fact, are in the part of the instruction which is decoded first and is available immediately. So if that's our instruction coming in, 1 cycle later, the reader ops can be sent directly over to the execute. That constitutes the reader phase as far as the execution is concerned. Meanwhile, the partly decoded instruction is sent to the second stage in the decoder and gets decoded there. And the ops resulting from that decode gets sent over to the execute engine. And the instruction moves to yet the 3rd stage of the decoder, where the writer ones are decoded and sent over. So the 3 cycles of execute directly correspond to the 3 cycles of the decode. As fast as things come out of the decode, even though it is all one instruction, that decode is stretched over 3 cycles, and correspondingly, the execution is also stretched over 3 cycles. The decoders are fully pipelined, and so as a result, you can initiate the decode of a new instruction every cycle. There's our first instruction going in. It produces a reader result and moves down, but meanwhile the next instruction gets pulled in. And its partial decodes go over to execution, and yet another instruction gets pulled in. And this becomes your steady state. At least if not interrupted by a branch misprediction, which is the bane of everybody. The phases of instruction decode overlap with the phases of the adjacent instructions. Reader phase happens in the same cycle as the op phase of the prior instruction and the writer phase of the instruction before that. Now, so much for the arrangement. How about those other phases? I only mentioned 3, but the phase listed several other phases. Well, pick phase, which is used by the pick operation, which is the question mark colon primitive of C, doesn't actually use the functional unit. It's not like an add, which has an adder. Instead, pick actually is implemented in the data distribution network called the crossbar, which communicates data across a cycle boundary from one cycle to the next. And actually, it occupies 0 time at all. Although the slide is showing that as if there was a pick functional unit, there really isn't. It's sort of actually happening as the cycle boundary happens and data is getting routed. So it doesn't occupy a functional unit, and we don't have to occupy a whole cycle for a pick. We can simply slip a pick in between an equal and a store. Call phase, used only by the call operation. Function calls within an instruction occur after any prior phase of the same instruction. And the remaining phases of that instruction are executed after the call returns. That is, what happens when you have a call is that the front half of the instruction is executed, then you do the call, and then the return comes back and you do the back half of the same instruction. If this is your source code, the machine code will look like that. Remember, the underscore means this is all one instruction. It's an add, a call, and a store. The add feeds, you'd think would be feeding some functional unit. What actually that function is in the called function, so that the result of the add is being passed directly into the call E with only just the cycle boundary in between. The callee will execute some amount. The double pink line there means some unknown number of cycles, whatever that function does. And eventually you'll execute a return. It will then exit, crossing a cycle boundary, and we're back in the original one, directly able to store the result of the function call. It's re-executed, but without the operations that have already been done. Well, what happens if you have more than one call? That works in ML. Multiple calls are executed consecutively in an order defined by the encoding order. And the returns from one call return directly into the next called function, not back to the original instruction. So if there's a piece of code where we have nested calls, the machine code will be add, call, call, store. And the add will feed G, which will run some number of operations in function G. That will return not back to the instruction containing the add, but directly into F, which will do some amount of work, which will eventually, the last guy in the cascade, will eventually return that value to the final store. Those of you who are familiar with the term will recognize that this is tail calls, and the mill does tail calls in hardware for free. That is a direct transfer, assuming, again, you didn't have a mispredict, which you would not have in this case. Now, that explains what the mechanism is, but what's the benefit? There have been a ton of papers and studies and vast quantities of academic arguing over exactly how much instruction level parallelism is inherent in existing programs. Many of these papers wind up, if you look at them very closely, that all they're doing is measuring their compiler or measuring their measurement methodology. But over time, for general purpose code, and we're not talking embedded, we're not talking the kinds of things that a GPU does, but for general purpose code, the consensus is that the operation level parallelism, that is the number of operations which do not have dependencies and in principle could be executed together, is in the order of 2 or 3 on the average. Well, it turns out that's false. In particular, out-of-order machines avoid it, but so does the mill. Say we have 2 data flows. These are, again, very simple for illustration. On a conventional machine, you could do the 2 cons in parallel, A cycle later, you could do the add and the subtract in parallel because there's nothing else which does not have a data dependency. A cycle later, you can do the two stores in parallel. Sure enough, operation level parallelism of 2. And it takes 3 cycles to do it. On a mill, they all go in 1 cycle. And the operation level parallelism is 6. Why? Because the con, the add, and the store can all be done in 1 instruction on the mill, and because the mill is very wide, it has no problem at all doing a 6-wide instruction. So we have effectively trebled our operation level parallelism. We call it Mach 3. Where the gain comes about. If what you have is a very long basic block and you're concerned about operations in the middle of the basic block, the mill's phasing offers no advantage over a conventional VLIW. Why? Assume that we're in the middle of a basic block and it's got some number of operations. With mill phasing, we would encode it this way. Note that the con will in fact wind up being executed there, and the store will wind up being executed there, but it's still 1 instruction as far as the code is concerned. On a VLIW, you can simply put the con and the store in the appropriate place. The mill has not gotten any faster than what the VLIW would have done. This, however, is true only in the middle of a long basic block. If you are not in that circumstance, when you're adjacent to control flow, phasing does earn cycles over a conventional AIW. If, for example, the basic code is there's a branch, and say it's an if-then-else, and the then part is doing our con-add store and then doing another branch to someplace else, well then, mill phasing will move the con up there, and that is true only if that branch is taken, if the encircled branch is in fact taken, because only then does that instruction in the then part actually happen, and only then does the con wind up actually having already executed in parallel with the branch. Similarly, the store in mill phasing will be at 1 cycle later, but even though there is a branch there, the exit branch, that store will be executed whether that branch is taken or not. In effect, mill phases get moved over control flow. On a VLIW without phasing, you can't do that. The only way you can get the con to be executed only if taken on a VLIW if it's in an instruction after the branch. The only way you can get that store done on a taken or not basis is if the branch which does the exit is after the store. The VLIW scheduler cannot hoist the con over the branch or lower the store over the branch, because if it hoisted the con over the branch, then the con would be executed whether or not the branch was taken, and that's not going to be semantically what the program asked for. And if it lowers the store over the branch, it will wind up only executing the store if the branch went one way rather than going the other way. So fundamentally, a VLIW is stuck and cannot do this kind of mechanism. Phasing, in some ways, is like out of order. It approximates data flow. A true data flow machine, those of you who are interested in history can look up the Manchester MU5 and find out what a real data flow machine might be, but no machine can be fundamentally faster than a data flow architecture. It's simply architecturally, mathematically impossible. Unfortunately, a true data flow architecture requires unbounded hardware, and that's rather difficult to fit on a chip. Consequently, all machines attempt to approximate what a data flow architecture does. And out of order does do that. It dynamically detects the presence of a data flow in the instruction stream and then schedules things in data flow order with maximum overlap. That's what your Haswells and so forth that do out of order do internally. Phasing, in many ways, can be thought of as being a statically scheduled out of order. The compiler knows with the data flow. The compiler doesn't have to go and figure it out in hardware the way an out of order machine does. And the compiler can simply schedule the operations such that the data flow that the operations represent properly overlaps with the data flows being scheduled by other instructions. The phasing device, because it doesn't have any benefit over VLIW in long codes, in the middle of long codes, it benefits you only when you're adjacent to control flow. However, control flow is exceptionally frequent. On the average, every 6 to 10 operations or thereabouts. Guess what? 1 mil instruction is quite happy with 6 to 10 operations. So one of the characteristics you see in mil code is that basic blocks tend to be 1 instruction long, the whole thing, no matter how much work it's doing. OOO, out of order, beats phasing when the actual dependencies of the data flow are not in the phase order. The phase order is fixed on a mil. You can't change it. So, for example, a function call whose argument is an add is one cycle on a mil. But an add, one of whose arguments is a function call, has to be 2, because the call phase is after the op phase. And OOO, which is dynamically detecting this and dynamically scheduling, can do a better job in that case. Turns out, well, we've done our best to order the phases in such a way that this kind of thing doesn't happen very much, and we've been reasonably successful. The performance is a rough approximation to what an OO machine will do. Phasing beats out of order when the out of order machine is issue limited. The mill is very, very wide, and out-of-order machines are hitting hardware limits which preclude having issue widths of more than about 8. Haswell, I think, is 8, for example. So if you want to be able to put together data flows which together would be a dozen operations, you're issue limited. You can't do that on an out-of-order machine. And furthermore, you're not going to be able to do it on any out-of-order machine because out-of-order hardware is extraordinarily complex, extraordinarily large, and extraordinarily power hungry, and you've just hit diminishing returns, and even 8 is pushing it. MIL does not have these constraints. It is extremely power stingy, and it puts its area into functional units which are tiny. So the MIL does not have constraints that make it issue limited, or at least family members don't. So phasing is an example of something that of which we've had other examples addressed in various talks. One of those in the discussions of the memory system of memory introduced a notion called a deferred load that I won't go into, but remember your homework. And its consequence of a deferred load is that we can approximate the performance of an out-of-order machine without the power and area overhead of actually doing a real out-of-order. This is another example. We will rarely, well, it depends on the complexity of the code, but we will not often actually beat an out-of-order machine, but we will be roughly at a par in terms of total throughput. And the saving is in the power and the area. Now, So much for ganging, and which is the attachment of operations temporally. In addition, we need to address the possibility of combining operations horizontally, not temporally, but spatially. That also exists on the mill, and it's called ganging. It removes a source count limitation, which is present on essentially all machines. Architectures are designed in order to have to optimize the common case, and the common case is that you have operations that are 2 input and 1 output, like an add. And consequently, there are data paths to feed functional units, which carry 2 data in and 1 data out. So nearly everything has that kind of a structure. Bear in mind, we're using the belt, so the value data is coming in from the belt, and but it's 2 in, and the adder takes in 2 inputs and produces 1 result, which goes back out. The operations are encoded. The bit layout of the encoding is designed to support this. The data paths are designed to support this, and essentially all machines do this. Us too. Unfortunately, there are operations that are exceptions to the 2 in and 1 out rule. One of them is fuse, multiply, add. It has 3 inputs and computes A times B plus C. Well, you might think you could do that. In fact, adding a 3rd input into the encoding and into the data paths to the functional pipelines would be really expensive, and fundamentally you don't want to do it. Every machine that supports FMA has to deal with this, and the contortions that it uses are extreme. If you want to get into the details, feel free. The mill doesn't do it quite that way. Instead, we define what we call a gang. These are 2 or more adjacent 2-input data paths that cooperatively implement a single operation. Those are two inputs. Each of the execution pipelines has a perfectly normal 2 input, 1 out, well, no outputs, 2 input, 0 output on the mill encoding slot. And each contains perfectly ordinary 2 input data paths suitable for functional units like ALUs and FPUs and so forth. When what you want to do is a 3 input, those slots cooperatively implement a single operation by defining another operation, whose name internally is called args, that has inputs but no results. Well, we now have 2 inputs going down one path and 1 input going down another path, but what we really want was 3 inputs. So args passes its data horizontally between the functional units. That in turn produces a result in a perfectly ordinary way. Ganging is used for all operations that have got more than 2 inputs. However, just having an argzop which does nothing except take in an input for the data path and pass it along horizontally seems somewhat wasteful. It'd be nice if you could do something else besides having the FMA there. So what's really going on? Well, internally to the FMA functional unit, there's a multiplier, and the 2 inputs get multiplied. Then the args value comes in, and the result of the multiply and the result of the value coming from the args gets passed to an adder, which is also in that same functional unit, like so. But we could do something useful in the second slot. So let's gang together 2 FMA units to make what we call FMAS, or fuse, multiply, add, subtract, with 4 inputs. The 2 pairs of units each go to the multiplier. the result of the two multiplies are horizontally interchanged. And then one side does an add, and the other side does a subtract. The result is two results. Mill is very good at multiple results because of the belt structure, which compute the sum and difference of two products. Sometimes you only want one, you ignore the second, or you sometimes want both for many kinds of floating point computations. It happens to like having both of those. Yes?
Do I recognize that as an FFT butterfly?
I'm somewhat deaf, and I'm going to need someone to repeat the question.
Is that an FFT butterfly impact?
Fancy that. In any case, sum and difference of two products, making use of the functional units that are already there. Now, I got backed up somehow. Alternatively, you could use that same hardware, there's two multipliers and two adders, to do two FMAs. Here we need 6 inputs. Okay. We're now going to get two individual FMA operations. FMAS, like FMA, has only one rounding error and is consequently is advantageous over the equivalent simple multiply add sequence. Now, ganging, as I said, is used for any time you need more than two inputs, but it actually has other uses as well, and I'm going to touch on one of those, which we call predicate gangs. Let me introduce you to the bane of CPU design. It's called a condition code. Condition codes are side effect byproducts of ALU operations where bits are set typically in the program status word that indicate whether the add you just did had a result that was 0, greater than 0, less than or 0, had a carry coming out of it, overflowed, or what have you. The problem is that this is a global state. It's real nice. You can do a subtract and get the subtract result, and in addition, immediately branch on whether you'd gotten to 0, for example. The condition codes were designed to support decremental looping. But the next operation that comes along that uses the condition codes just clobbered your condition codes. And when you are doing a whole bunch of operations in parallel, all of whom set the condition codes, well, who wins? Who does set them? And so condition codes are never used in wide issue machines. In an out-of-order machine, condition codes have to be renamed because of the problem that they will get cluttered. The add and the subtract are not necessarily done in the order that they look like, and you have to have multiple copies of the condition codes that moved around like multiple copies of the registers, and it's part of the extremely complicated and power-hungry part of making an out-of-order machine work. All of the people who actually have to do things like modern x86 chips do dearly wish the condition codes had gotten left out of the original architecture, but the original architecture did not have that much of a view of the future. On the other hand, condition codes will speed up some kinds of code, but they can't be speculated because it's a global state. The mill is very big on speculation, making use of all of its width. You just need to be able to collect the predicate metadata of was this greater than or less than 0 or what have you, and save it somewhere where somebody can use it without actually saving it globally. So say that's our source code, and this is the typical bottom of a counting loop. Are we at the end of the loop the piece of code? We decrement I, and if it's greater than 0, we will go to the top of the loop or do something. In machine code, if there are no condition codes, you have to do a subtract on the I to decrement it. And then you separately do a greater than 0 on the result. and then you branch if that greater returned true. True in this case being a data value rather than a condition code. With condition codes, the subtract sets the greater than condition code, and the branch can simply branch on that condition right away. We've saved a cycle. That's why condition codes exist. The problem, of course, is that many operations set the codes, but they're rather rarely looked at, typically only by a branch immediately following them. The condition codes are almost always immediately consumed and are never cared about anymore, but somebody has to keep track of them in the hardware. And they can't be speculated because it's global state. So down with condition codes. In the words of Edgar Dijkstra, condition codes considered harmful. So what you really want is to be able to speculate them. Well, the mill code, we need subtract and greater than branch on true. That is, in fact, one instruction. We want a data flow that goes from subtract to greater to branch on true. But subtract and greater than are both op-phase operations. Consequently, that's a no-no, and you can't do that. Instead, it would require this code. We at least get the greater and the branch done in parallel due to phasing, but we're still not much better off than what your typical RISC machine would be. One possibility would be to have the subtract produce true results, or at least some flavor of subtract to produce true results, both the numeric result of the subtract and also a flag saying it was greater. Well, we could define such an operation, let's call it subtract greater, that returns both the difference and a Boolean as two different results. That works. It would look like that. Now we're just in one instruction. It's up phase and rudder phase. Everybody's happy. Except you wind up with a huge opcode explosion because for everything that might produce a condition code-like result, you now have to have flavors that produce each of the individual possible conditions, and your opcode space, the bit space in your encoding, winds up getting rather nastily cluttered with stuff like that. An implementation of this would require the addition of another fast path in the actual encoding. The actual mechanism passes data back and forth. That has clock impact. Don't worry about the details. That gentleman up there next to the camera can explain all about it, but he's the hardware guy that can do so. But fundamentally, there's good hardware reasons why you don't want to do this. So that isn't going to work. Solution. We gang a predicate. The ALUs unconditionally and always provide what would be a condition code set horizontally to the adjacent slot. Then we define one operation, greater code, which reads the greater bit and returns it as a bool. This is our source code. That is our mill code. The underscore means it's all one instruction. That is a gang. It is not passing data through the normal data flow. It's passing data across between functioning units within a cycle. And that data in turn can be passed to the branch due to phasing. The gang is op phase. The gang may be just thought of as being a two-slot super operation. There's just one operation, even though we had to break it apart into two pieces. There's the two inputs to the sub. The greater has no inputs at all. The code gets passed from the sub to the greater horizontally. We go through the cycle boundary. The subtract result winds up everywhere it does, as does the greater result. But in addition, the branch on true can pick up that. It's all one instruction, and we're done. Phasing permits us to pick that up as being still in the same cycle. Consequently, because these are numeric predicates, they get dropped in the belt like any other, just as if we had a two-result operation, except that what we actually have is two different slots producing one result each, so we don't have fast-pass problems, and we don't have encoding explosion problems, and speculation is done. Now, there's some operations that while you'd like to be able to issue them in parallel, they cannot execute in parallel, and control flow are the most important of these. We want to be able to have a bunch of branches in one instruction, multi-way branches. The typical example being a switch or a case statement, depending on your favorite language, which tend to be truly annoying in hardware. If that is our source code, the machine code will typically test for the first case and branch to it, test for the next case and branch to it, test for the next case and branch to it, and so forth. If the cases are dense, sometimes you can load a dispatch table, a table of label variables, or a table of branch offsets, but that involves having to pull stuff out of memory, and that's slow, and well, there are a whole lot of solutions, none of them very satisfactory, that you'll find in architectures of various machines. Typically, however, most compilers today will turn this into a chain of individual if tests, though they will optimize certain cases. The problems are that the tests and branches execute sequentially. You're going to wind up with a prediction for each of those branches, and they tend to clutter the prediction tables. It's possible for the sequence to mispredict several times because the predictions will zoom down and say, oh, this must be case 3, and we'll send the execution unit off to the corresponding case. It's discovered that this is wrong. We unwind everything, go and test the next case, and in the absence of 3, it now predicts that 5 is going to be taken, and it turns out that 5 wasn't taken either, and the correct thing we should have done was go to the default case, but meanwhile, we've taken the 2 mispredicts, and mispredicts on a conventional machine are exceptionally painful. The mill only has a 5-cycle mispredict penalty as opposed to the 15 or 20 typical of other machines, but 5 cycles is painful for us too. So, what we do is we put all of the thing in one instruction. The equals feed only their respective branches. They can be done in parallel because there's no data connection between them. They're both up phase, but they both can be executed simultaneously. The data will flow to the 2 branches, which are both in writer phase. They don't have any data interconnection, so they can be executed in parallel. However, of course, only one of those should win. In this case, numerically, only one is possible, but indeed, other conditions, it could be that more than one had its taken, untaken predicate true. We define a rule such that in encoding order, the first taken branch is taken, and if there are more, we don't care. So the first encoding, even though they're all executed, only one actually reroutes the core execution, the first one. There is only one prediction for the whole switch. The mill predicts exits rather than branches, and that has been thoroughly covered in a talk called Prediction that you will find in your homework assignment. No more than one mispredict is possible. By the time we come back having discovered that we were wrong, we now have got the correct value and only we will in fact take the correct branch. So, in brief summary, you can do intra-instruction data flow. If every phase is occupied, you can wind up having a substantial expansion, but in practice, codes do not contain every phase in a data flow. We find that a Mach 3 is reasonably representative. It is heavily dependent on the application and the nature of the code, and it's also dependent on the width of the particular family member. Low-end machines, low-end mills do not have all that much width, and there might be implicitly parallelism available that we can't use because it's not enough functional units. At the high end, it tends to be not a problem. Single instructions are issued over 3 cycles. Effectively, what we have is pseudo out of order that executes operations over control flow the way a hardware out of order does. We can have instructions containing multiple calls, which means the data flows can contain multiple calls too. Cascaded calls are automatically tail called. Only the last one returns to the original instruction. There's n-way branching in one instruction, and the compiler and the hardware both know what's going to happen and schedule the code accordingly. We're not constrained by pipeline data paths because we can gang, assuming that the underlying functional capacity is there. Consequently, we can support novel operations which have M inputs and N outputs that other machines simply do not have, including perhaps specialized operations for certain particular market areas. And has speculatable condition codes. So you get the performance gain on it without global state. There, I will leave this slide up. There you can find additional documentation. The mailing list will get you on our mailing list for announcements of talks like this, which take place, sorry Andy, takes place elsewhere. Although you could sign us up for another one next semester if you wanted. And there's announcements of things like the white paper availabilities and such like. I'm open to questions.
Is there an LLVM compiler for your machine? And is it possible to slurp up real code and?
We're in mid-patent filing, so we cannot expose a bunch of stuff. The things which I will talk about in these talks are things the patents have gone in, but to completely expose the machine, we cannot yet do. That said, that doesn't matter because the compiler doesn't work. We had a compiler which was based on the EDG front end, the one which goes into the Intel ICC compiler, and our own middle and back ends. And it was up to the point where it would generate code. And we realized that this was completely wrong-headed. We do not want to roll our own, especially not all the middle end optimizations for vectorization, which is well-established technology, and there's just no point in us repeating it. And so we made the decision to convert discard our old one and convert to LLVM. That was at the point when the patent office changed its rules, and we realized we had to come out of stealth and immediately start filing patents. And frankly, I am so sick of patents because we've been doing nothing except file patents for the last year. And unfortunately, the LLVM effort has been set aside. We just recently added a new person to the team who's taking that on, and there will be some major work having to be done even with LLVM, because LLVM makes some very rash assumptions. For example, it assumes it's running on a register machine, and we are not. But we have done enough work to know where at least some of the bodies are buried in LLVM or mill on the LLVM. It is definitely a major piece of work still to go. By the time, however, that work is done, all the patents will be in, we'll have benchmarks available and all the rest of everything else. So it doesn't really matter because we have two blocked things and they'll come out the back end roughly the same time, we think. We hope. I'm a compiler guy. I've done 11 compilers, so there's a lot of work in there, but we believe, in part because we already did one of the compiler, we believe we understand what the issues will be, and our major difficulties will in fact be not with our stuff, but with LLVM, we think. More?
So for your typical machine, how many entries your belt would have, and how many ports, reads and write ports you need for belt storage?
Dave, can you come front and repeat?
Read and write. How many belt positions and how many loads and stores, you mean?
Read and write ports.
What do you mean? You mean load to memory and store to memory?
No, the belt.
On the belt? Oh, reading.
Yeah. It's a family, like the 360 was a family. These parameters vary by family member. The smallest one we have currently specified for configuration has a belt length of 8 operands. The largest one we have is 32 operands. It's pretty clear that there's no point in anything smaller than 8. It's not clear that whether 64 would be useful. We believe not. You want to have the belt size to track the number of functional units, because the number of functional units determines how many new values can drop each cycle. You have 6 adders, you can drop 6 add results. And you want to have enough belt so that those results get used before they fall off the end. So as you get more functional units, you also want to extend the belt to match. It's purely a pragmatic sizing based on SIM.
So is that correct that, let's say, for 30 units, if you have 30 units, you would have 32 registers in your belt, and you would have basically 90 ports.
Again?
At a 32 belt, you'd have 32 registers in your belt and 90 some ports.
Okay. These are not registers.
Well, they're registered in the sense of a flip-flop that has
There's not flip-flops. There's not flip-flops either. The belt has been discussed in a prior talk, and without slides or whiteboard, it would be a bit to explain. The conceptual model of it being a colossal shift register is false. It doesn't actually work that way. There is no colossal shift register in the thing. It is not implemented as an SRAM array. It is not implemented as a register file. Consequently, the notion of ports is not meaningful. You go do the homework page and you'll see how it works.
The only alternative is a multiplexer tree, a pipeline multiplexer tree, right? Oh. I mean, that's the one remaining. No.
The belt is essentially the bypass network that a conventional machine has.
Right.
It's mux trees. Okay? The way the addressing happens is through a naming process. When something which was formerly called B3 becomes B5, all this changes the name. No data bits have moved.
Time has passed. Time passed, which caused the name to change.
Yes.
So with 8 belt positions or 16 or 32 or whatever, the equivalent of object code that's running on the machine would have different size fields depending on...
Oh, yes.
Also, it seems that at some point things will fall off the end of the belt. And there will be cases where you haven't used it yet, so presumably they will fall into holding registers.
I'll address both questions, and I could hear you. I'm sorry, folks, I'm slightly deaf, and I need some help. with respect to things falling off the end. Separately, there is a facility called the scratch pad. This is not memory. It is an operand store. It retains values in internal format, which is not the same as a memory format. And there are operations that say this value on the belt, park it in the scratch pad, and later on another operation that says get it from the scratch pad and drop it on the belt. So values which need to be kept for long term, because their use is not yet coming up yet, or their last use is not yet coming up yet, wind up being explicitly moved to the scratch pad. The great majority of operands that are produced are immediately used once, and immediately they're immediately dead. Register death in a register machine is extremely high. There'll be some kind of case. People will use a register as fast memory, but for things which are actually intermediate results, they tend to, if your compiler is doing a halfway decent job of scheduling producers adjacent to consumers, their lifetime is very brief, and the great majority of them, if we've sized the belt appropriately, the great majority of them will fall off the belt because they're past their last use. But for those that are, they get dropped to the scratch pad. And the other, encoding. Not only does each family member have a unique binary encoding, but each encoding slot has a unique binary encoding. If this slot has got an ALU and an FPU, then it has to support both integer and floating point operations. And our software produces a binary encoding that encodes both integer and floating point operations. The adjacent slot, which has only got an ALU and not an FPU, has its own unique encoding that only contains the integer operations and not the floating point operations. These encodings are mechanically generated from a specification. Nobody does this by hand. Nobody lays out bits. The specification simply says in this slot is this functional unit, and separately that functional unit supports blah, 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 and blah. And the software, which has been running for years, this is long, stable software, proceeds to produce a entropy optimal encoding with some special things so as to improve the life of the decoder beyond simple optimal entropy. And that's mechanically generated. And a trivial change, you got a completely different binary encoding. The way you're able to handle binary portability, which of course is important, is the same way that it's done in the IBM AS400 and its descendants. And that is that what actually appears in your load module is a member-independent representation of the program. And at install, or potentially load time if it's that late, or if you're building a ROM, a program which effectively is the last phase of the compiler, we call it the specializer, translates the member-independent representation of the program to the actual bitsies for that member. That targeted member-dependent representation is then cached in the load module. The next time you run it, we simply pull up that binary. But if you take the file off to another machine, the loader will look and say, oh, you don't have a cached version of my machine. Runs the specializer, kind of like dynamic linking. It runs for you for free. Cache the new one, and there's the equivalent of a strip tool, which will remove excess cache ones that you don't want to save disk space and so forth. Okay. There are many. The mill is a wide issue machine in the sense that a single instruction can contain many operations, like a VLIW does. Fair warning, a terminological trap here. Most people are used to thinking that an add is an instruction. Once you're in the wide issue world, an add is not an instruction. An add is an operation, and there may be a ton of other operations in the same instruction. So in this case, you can have 3 different functional units, which will be independently grabbing values off of the belt. And in due course, when those functional units are ready to retire a result, all of their results drop onto the front of the belt and push corresponding numbers of operations off the back. Addressing into the belt is addressed by relative position. So this, for example, might be an assembly language operation. This says add B3, belt position 3, to belt position 5. Note no destination. The results are implicitly dropped on the front. The B3 and B5 are there. If you think about it, you realize that B3 is the 4th most recent value to have dropped to the belt. And B5 is the 6th most recent value to have dropped to the belt. So this is temporal addressing. It is not spatial addressing. You're not saying put something in R6 and it stays in R6. This says pick up the value indicated by the temporal order in which it got originally placed upon the belt. So a consequence of available on the 380 website and on ours, and much greater detail at other locations. Given that as a background, I'll talk a bit about how phasing permits us to triple the effective ILP, instruction level parallelism, of existing codes, how we are able to combine the computational capacity of the machine so as to support novel operations that a conventional machine cannot do. And how that gets used in order to avoid the problems using condition codes to indicate Boolean values. Lastly, I'll speak briefly on the subject of how n-way branching is performed and how when you have multiple calls in a single instruction, how these cascade. This is a series of talks. This is the 6th of them. All the prior talks videos are available on our website at that address. Those of you who are taking the class for credit, your homework assignment is to review the material at that location. There will be a test. And a caution. This talk is a gross oversimplification. The guts inside a CPU are fiendishly complicated and depend on hardware and other details that cannot be covered in a talk of this nature. Instead, I try to convey an intuitive understanding suitable for a non-specialist. You're assumed to have some idea what goes on in the CPU, but we're not going to this, is that every time you do a new drop on the front, everybody's temporal address changes. So that, for example, if we want to reference that value 8 in red there, that is B3 now. But as soon as a few more values drop onto the belt, B3 now refers to somebody else, and that value 8 is now B6. This is a truly awful process to attempt to keep track of by hand. The mill is not designed to be an assembly language target. However, this is trivial for a compiler to keep track of, and it is no more difficult than the problems involved in, for example, register coloring and similar things for a compiler. Now, so much for the belt. Going to talk about phasing. Operations connect through data flow paths such that the result of one operation is the input to a next. And the chain of such items is a data flow, frequently a data tree, but for most of what I can show on a slide, you can only fit so much on a slide. We're going to be looking at linear data flows rather than trees. A consequence of the way the mill is organized is that we are in fact able to execute faster than the clock rate would appear to make possible. I want to emphasize that this is a programming model. The underlying reality does not have a time tunnel inside it. There is no black hole and a spinning black hole that permits you to Today's talk is about certain aspects of the execution model used by the mill architecture. The mill is a family of CPU designs, family in the sense of the 360. Due to the advances in the architecture, it's a commercial product, or we hope it will be. It's still in development. And it offers a 10x power performance advantage over existing architectures. This is an architectural advance. It is not a circuit advance. It is not a fab advance. We use exactly the same run-of-the-fab circuits and standard rules as anybody else. It is an architectural advantage. It does so without requiring a rewrite of your program. It does so without requiring multiple core or multi-programming. You can, of course, multi-core and multi-program mills just like anything else, and it's just as much a pain in the butt on a mill as it is on anybody else. This particular talk, I have to back up a little bit and speak a little bit to describe the way data is moved back and forth internally to the machine. The mill has no general registers. It uses a different device, and I have to explain that a bit. This was actually covered in considerably greater depth roughly a year ago, May or thereabouts, here, and the complete talk of that is both going to get in any great detail. I'm open to questions after the talk, and I can go into all the detail you'll ever want, but the talk itself doesn't do that. Reality is much more complicated than this talk will indicate. We try not to oversimplify, but sometimes. So a few words on the belt. As I said, the machine has got no general registers, but you do have to get the result from one add into the multiply that you have to use the next data with, and that requires a communication device. The mill is the first of a new category of processors called a belt machine. There are numerous other categories. There are stack machines and accumulator machines and general register machines and so forth. These are categories. There's lots of different architectures within a category. There's lots of possible belt machines. The mill is one. It is a point in that design space. The communication device looks like a conveyor belt. It is a fixed length FIFO. Assume that that is a set of values sitting on the belt. A functional unit can read any position in that FIFO, pulling values off it down into the functional unit. New results always drop on the front of the belt, unconditionally. You do not specify a destination for your computation. However, it's a fixed length, so when you drop a new one on the front, well, that pushes the oldest off the back, and it is gone permanently. The functional units,